I'm sat alone in a boggy marsh, totally motionless except for her heart. Mud flowed up into lumps, pajamas. She totally confused all the passing piranhas. She's lump, she's in my head. She's lump, she might be dead. Lump lingered last in line for brains, and the one she got was sort of rotten and insane. Small things so sad that birds could land. Is Lump fast asleep or rocking out with the band? She's lump, she's in my head. She's lump, she might be dead. Lump was limp and lonely and needed a shove. Lump slipped on a kiss and tumbled into love. She spent her 20s between the sheets, and life limped along at subsonic speeds. She's lump, she's in my head. She's lump, she might be dead. Is this lump out of my head? I think so. Is this lump out of my head? I think so. Yeah. Woo. Is this lump out of my head? I think so. Is this lump out of my head?
All right, so welcome back. Today we're going to continue. In fact, we're going to finish up strings, our string discussion on processing strings. You've already looked at a little bit of processing in that you can, iterate over a string. At least in C, you can iterate over a string and, change the contents of it. You can use the C type library in order to, do certain things. For example, let's see, where were we? You can check that it is a space and then, change it. You can change things to upper or lowercase if you really want to. You, of course, can, truncate a string by simply just putting in a null terminating character in C. In Java, you don't treat strings the same way. You treat them as almost first-class citizens. Just use what, the built-in operators for concatenation. Use string builder if you actually want to have a mutable string, et cetera, et cetera. So what we're going to do now is we're going to look at more ways of processing strings. In particular, we're going to start with string formatting. So in C, we're looking at more string processing in C, and then once we get done with that, then I'll show you how to do all the same stuff in Java. So recall that you can use Printf to format a output that gets printed to the standard output, DARD output, right? You can also use sprintf, to format to a string output, right? So if you don't want this printed to the standard output, you can have it printed to a string, in other words, just stored to a string. So let's go ahead and take a look at the signature here. If I look up the man pages on sprintf, what does it look like? Give myself some more room up here. Of course, you can see that we actually have a lot of versions of Printf that we're familiar with. There's sprintf that we're about to look at here in a second. There's also fprintf. Our next module is on file, input, and output. So what do you think that F stands for? File print. Instead of printing to the standard output, you print to a file that gets saved on the disk or something. Yeah? I forget what that is. I'd have to look that up. I think that they are byte-limited versions, so that they're a little bit safer. If it doesn't fit into the buffer, then it won't overflow the buffer. But don't quote me on that. I think that that's what it is. But let's go ahead and take a look at sprintf. Kind of like a byte-limited version, kind of like strncpy and strncat, right? Here's the signature. And, oops, let me codize that. There we go. So, it's like printf in that it takes a format and then it's a variadic, it takes a variable number of arguments after that. But the difference here is that it takes a string. It's a non-const string. We don't have a const in front of it here. So that tells you that it's going to be making changes to that string. Right? This integer, you don't have to worry about that. That's going to be the number of placeholders that it actually matches. You can use that for error checking if you really want to. So let's just go ahead and do it by example here. What I'll do is I'll go ahead and create my first name. So char first name equals Chris, right? And char last name equals Burke. And what I want to do is I want to format this last name, comma, space, first name. And so if I were to do this with printf, of course I would go %s, comma, space, %s, and then print last name and first name. There we go. When I run this, oops, there we go. Of course, I get that kind of output. Right? There's no end-line character here because I didn't put an end-line character. So what does it look like to print to a string instead? I would have to put a string as the first argument here. And of course, it also means that I would have to create that string, and it would have to be big enough to hold the contents that I actually want to print to it. So char full name, or formatted name, whatever you want, is going to, I'll just make this big enough. Right? That's way more than I'll need to hold my first name, my last name, the comma, and the space, and the null terminating character, but so be it. Yeah, go ahead. It will, as long as there is enough space. So the only assumption that you have to follow here is that it's big enough to hold what you're trying to print to it. Right? So now I'll show you that this actually worked. Hello, %s, and the line, and I'll print out the full name. And you'll see that it prints out the formatted name just like I had down here. So all the knowledge that you have about printf, all you need to do is import that knowledge, and you can now print to a string. If you want to print to a string and then dump that string to a file, print to a string and then dump that string to the standard output, you can do that. If you want to dump that to a string and then further process that string, you can do that as well. Okay? I'll go ahead and make sure that you have this in the notes as an example. But otherwise, same placeholders, same everything that you would do with printf. You can use the formatting, you can go out to a certain number of decimals, etc. The only thing that you have to be careful of is that sprintf assumes that the destination string is big enough to hold whatever you are printing, whatever you're trying to print. So one common pattern is to create a string that is bigger than you'll ever need. Right? But of course you can't go too big because this is a static string, and it would end up overflowing the stack. But you can make it reasonably big, like say 100 is big enough for most names. And then you can, if you really want later on, you can go ahead and create a dynamic string that is exactly the size that you want. So for example, I could, instead of calling this full name, I could call this what's called a buffer. A buffer is simply just a temporary space where you put data temporarily, and then you process it later. So I will temporarily put this into a buffer. After that, I'm wasting some bytes here, right? I'm wasting, let's see, there's 5 letters in my first name, there are 6 letters in my last name, plus the 2 letters for comma space, plus the null terminating character. Altogether, that is 11, 12, 13, 14, right? I don't want to have to do that math, though. Right? So what I'll do is I'll dump it to a buffer, and then I'll create a dynamic string that is big enough to hold my first name, or my full formatted name, excuse me. So char star, full name, is equal to a call to malloc. And I want a number of characters. How many do I want? I want string length of whatever is in the buffer, plus 1. Why plus 1 again? The null terminating character, right? And then I can go ahead and copy it over. strcpy into full name whatever was in the buffer, and then you can delete the buffer if you made it dynamically. Don't delete the buffer if it is a static string, of course, because then you are trying to delete or free up your stack space, and that's not going to work. But this is a common pattern that you can use to create temporary buffer space, so you don't have to do, well, there's 5 here, plus 6 here, plus 2, plus 1, plus whatever, right? You don't have to go through all that, annoying arithmetic. Right? And you see that it's exactly the size, okay? I'll make sure that you have this in the notes as well. Right? So common pattern, you can use a temporary buffer that is big enough to work with, then create a dynamic string of the exact size you need. So again, the example that we just did, there you go. Okay. Another common task is tokenization. Sorry. String tokenization. So often, data is formatted, right? CSV data, TSV data. These are all called flat file formats, right? For example, CSV is what we're going to be focusing on. CSV data stands for comma separated value data. And if you've ever had a file that looks like this, you have data tokens. On each line is one record. And each line, you have tokens. Here's here's an example. Here's information about myself. There's my first name, comma, my last name, comma, my NUID, comma, right? Comma separated value files. TSV, what do you think the T stands for there? Tabs, right? Tab separated value files, right? Or you could have semicolon separated value files, or colon separated value files, like that we'll look at next week when we do some file processing. Yeah?
Is there line separated?
Generally, the lines are used to denote records. So record 1, then the next line, record 2, record 3, record 4, etc. Blank lines are sometimes used to delimit, say, headers. So here's metadata up here, blank line, and then you know that the actual data starts down here. HTTP, the protocol, uses that. Yeah?
I was just wondering, like the dictionary we used in the lab yesterday.
That was 1 to a line, but there was only 1 token per line, because if it was like a word, comma, definition, comma, variations, right? If it was a full dictionary, then you could use comma separated value files. But the dictionary that you used yesterday was just 1 to a line. And it was processed line by line, right? So with CSV data, of course, it's kind of like an Excel file. In fact, if you have a CSV data file and you double click it, most often it'll ask you, do you want to open this up in Excel? And then you've got rows and then you've got columns, and it automatically separates these into different columns. How do we do that in code, right? So the way that we do that in code is by processing. Suppose that we just have 1 record now, right? You want to process the record token by token, right? What's a token? A token of data is separated by a delimiter. In this case, the delimiter is the comma. It separates the first token being my first name, then the second token, third token, fourth token. And I want to do all the tokens, right? So the way that you can do this in C is you can use a function. In C, you can use a function called strtoke. What do you think that stands for? String tokenization, right? You're tokenizing it, right? That splits a string into their separate tokens. There we go. So here is the function signature. Let me increase the size here a little bit. So let's look at each one of these things. The first argument is the string you want to tokenize, process, right? Tokenize. There we go. Note the first argument is not const. What does that tell you? It's going to change it, right? strtoke will change your string, right? And that's the reason that why does it change your string? Well, the way that it works is it processes it and it says, okay, that character. Oh, there's the first delimiter. I'm going to put a null terminator there and return this token back to you. So it ends up taking out all of your delimiters and throwing them away and replacing them with null terminators. So if you don't want that to happen, if you want to retain the original data, what do you need to do? You need to take that data and make a deep separate copy and then process that copy. And this is one use case where you would want a deep copy string like we covered on Tuesday. Yeah?
Is the 103 store supposed to be separated by a comma?
Nope, no, that's my office number, 103 Shore. Right. I mean, you could, then you have the office number and office building if you wanted to, right? Just like an address. Do you want the whole address or do you want, street, comma, city, comma, state, whatever, right? And that, it all depends on the format that you were expecting, right? The second is a string containing delimiters, right? Now, I put an S here because what you can actually do is you can use multiple delimiters. If you want to delimit on commas and tabs and semicolons and colons, if you really want to, you can do that. We're going to keep it simple and we're going to keep it, restrict our attention to just one delimiter, but it still has to be a string, all right? It returns a pointer to the next token, right? Beware. The first time you call strtoke, you pass in the string you want to tokenize. Right? The second time, or each subsequent time, I should say, each subsequent call, you pass in null to continue processing the same string. If you pass in a new string, it will just start over on that new string. If you pass in the same string, it'll get stuck and it'll always process the first token. First token, first token, first token, first token. So let me go ahead and copy this data over here so that we can actually process it, and I'll show you how it works. Right? So get rid of all of this stuff. There we go. And char data is equal to this. Okay? I want to process this token by token. Char token. Because strtoke returns a char star, the token that you actually want to process. Okay? What do I want to process? I want to process data. And what is the delimiter I want? Well, for now, let's just go ahead and restrict our attention to a comma. Okay? And we'll print it out. Token is equal to %s token. Okay? Let's go ahead and see the results of this, and you can see that the first token is Chris. How do I get the second token? Well, I call strtoke again. Token is equal to strtoke of data. There. Now remember, each subsequent call, you don't pass in the same string. You pass in null to continue processing the same string. If I do this, then you'll see that it just processes it over and over again. Right? It doesn't matter how many times I do this, it's still going to continue starting over from this string. So I need to pass in null on each subsequent call in order to go over to the next string. And when I do this, you see the next string. Right? All right, how many tokens were there? I think there were 6. So 1, 2, 3, 4, 5, 6. Right? Copy pasta. Right? And it works. But what if I go, oops, come on. What if I go one more? What if I go 7? So, what does it return for that last token? When there is no last token, right? It only goes up to 103 Shore, and then it's done. So what did it end up returning? Null, right? So strtoke returns null when there are no more tokens to process. This suggests that I don't have to do copy pasta, copy pasta, copy pasta, right? All I have to do is what? A while loop. While the token is not null, oops, I'll go ahead and print it out and call strToken again to set myself up for the next iteration of this loop, right? When it's null, when it's done processing, token will be null and we break out of this while loop, right? And now I'm only processing exactly what's there, right? First token, second, third, fourth, fifth, sixth. And then at the end, it returns null, we break out of this while loop, right? So right now, by processing the token, all I'm doing is printing it out. Of course, you could do something more complicated, like making a deep copy of it and putting it into a file, whatever you're trying to process, whatever process means, okay? All right, what happens when I expect, say, 6 tokens, but I get 7 or something like that, like some mysterious foo in here, right? Well, it is going to process it, and it's going to give me 7 tokens. I'm expecting my first name, then my last name, then my NUID, but I don't get that. I know something's wrong here. You can always just check, establish a counter, right? Num tokens. I'll make it equal to 0, right? And then num tokens plus plus, right? And then I can check at the end. If num tokens is not equal to the expectation, 6, right? Then I know something went wrong. Printf, bad data, right? Or something like that. So, very simple ways of doing very simple data processing, right? We got bad data because we got 7 tokens instead. If I was expecting, say, this one to be an integer, then I could do more error checking. That the third token should be an integer. When I try to convert, it doesn't work. I can immediately stop and say bad data, right? Bad input, right? But this is basic data processing using tokenization. Now, in real life, in practice, it's way more complicated than that, because what happens if you've got a comma actually in your data, right? Well, now you have to escape it, meaning that you can't just blindly tokenize things anymore. You have to check, is this token a backslash, an escape token or not, right? And you have to be very, very careful about that kind of stuff. And then when you do one solution, that pops up other issues, right? Well, what happens when now you have a backslash in your data, right? Now you need to escape your backslash. Okay, well, what happens? Well, you know, it's a never-ending cycle until you get every single edge case and every single corner case. So in practice, don't worry about it. Bring in a library. Let the library do the work for you. Right? There are plenty of CSV data processing libraries out there. Okay. But we're going to keep it simple, and we're not going to throw anything like that for you, at you. All right? I'll make sure that you've got this in the notes. And let's check online for any questions. I don't see any there. None so far. Thank you for 14 people joining us today. Yeah. I don't know, does that include people in here? Oh, okay. Oh well. Many other people rewatch it later on, which is good. Okay. Finally, string comparisons revisited, because I think that we've done this before. String comparisons in C, right? In C, just like you did yesterday, if you did the C version of the library or of the lab, strcmp can be used to compare the contents of 2 strings. Right? You cannot use the equals equals operator to compare strings. Right? Remember that the equals equals operator is comparing memory locations. Is this string the same string as this one? Well, are they stored in the same memory location? Well, if they're stored in the same memory location, well, of course their contents are going to be equal. But you could have a string that holds hello and another string that holds exactly the same content, hello, stored in different memory locations with the same contents, and it'll end up being no, these 2 things are not equal because they're at different memory locations, right? So instead you need, and besides that, you still need to determine, I don't want to know just are these 2 strings the same thing or not? I want to know, given this string and this string, which one comes first? A and B, or they're out of order, B and A, or they're equal, right? I need way more information because, say, I want to sort the strings or something like that. And strcmp is your solution for that. The strcmp is like follows a comparator pattern. Right? It takes two arguments, A and B, and it returns an integer, right? Always an integer, because you can't say you can't have it like 1.5 or something like that. And the value of the integer is meaningless usually, but the sign of the integer is what you need to look at. It returns something negative if A comes before B. Right? It returns 0 if A and B have the same contents. Right? It returns something positive if A comes after B. Right? So this is a standard comparator pattern. It returns something negative if they're in order, A, B. It returns something positive if they're out of order. And it returns 0 if they're the same. It follows the number line. Negatives, 0, positive. Right? So A, B, that's their sequence in the number line. Just remember it returns something negative. If they're out of order, then it returns something positive. Right? That's the way that I remember all that stuff. Right? So let's go ahead and take a look here. Not here, but over here. Let's go ahead and establish two char A is equal to apple, right? And char B, I'll make them equal initially, right? And I'm just going to go ahead and cut and paste this. Right? And modify, forget about this for a second, strcmp. There we go. So what I'm doing is I'm creating two strings here. I'm calling strcmp and I'm grabbing its return value. If it's negative, that means that A comes before B. If it's positive, that means that B comes before A. And if it's 0 else, that's the only other thing that it can be, then they're equal. So if I've got apple and apple here, of course, come on, they're going to be equal. Right? If I've got apple and banana, then which comes first? Apple still. Apple comes before banana, right? If I switch them around, then of course apple comes before banana still, right? What about apple and apples? Which one comes first? So in a dictionary, would you actually have two entries, apple and then apples? No, you'd have an entry for apple, and then you would have plural form apples, right, under that form. But here we do have an ordering. Which one comes first? The shorter one, right? Okay, well, what happens when I do apple and apples, or apple and apple? Which one of those comes first? Good job. Good answer. Lowercase or uppercase? Uppercase comes first. Well, they're not equal. Right? Why is that? It's because all this stuff is lexicographic ordering. Right? strcmp uses lexicographic ordering, right? Not dictionary or alphabetic ordering. Right? It uses the ASCII text table values, right? Where capitals come first. In fact, if I give you banana, right, capital banana here, and apple, then which one of those comes first, according to the ASCII text table? All caps come before lowercase values. So banana mysteriously comes before apple now, right? Even though that's not the dictionary, right? That is lexicographic, right? You can do a couple of variations on this. For example, str case CMP compares lexicographically, but ignores the upper versus lower case. Right? It's case insensitive. Right? If I use case CMP here, now I get a different result. Apple, lowercase, will now come before banana because we're ignoring the uppercase, lowercase distinctions there. Apple comes before banana now. Right? Not only that, but you have another variation. Let me go ahead and go back to apple and apples. Right? I can do a byte-limited version of this called strncmp. If I only want to look at the first 5 characters, right? Now it'll look at apple, and it'll end its comparison. And of course, apple and apple, that's going to be the same thing. So they're going to end up being equal in this case. And that's strncmp. Right? strncmp is a byte-limited version. And then, of course, you can even combine these. strn case CMP is a variation that includes both. Right. So you can, I don't know, can't think of a good example. Banana and banjo. There we go. And if I only compare the first 3, ignoring case, what's it going to print out now? If I only compare the first 3 characters, ignoring the case, those two things end up being equal. Right? Weird, but sometimes you use that kind of stuff. Right? All right, so we covered today formatting, string tokenization, and string comparisons. How do we do all this again in Java? And as you can imagine, it's going to be way easier. Why? Because of the Java, of the way that Java treats strings. So formatting, to format using Printf style printing, formatting, formatting, you can use string.format. Right? I don't know why they didn't just go with string.printf, but they didn't. Right? So for example, let me go ahead and pull what we had before. Actually, no, I'll just do it like this. If I want string first name is equal to Chris. You know what? Yeah, let me go ahead and cut and paste this, because I do want to show you the distinctions between the 2 languages. Right? First of all, we don't have character arrays. We have full classes to do this. So, string last name. All right? We don't need buffers anymore because Java takes care of creating new strings for us. Right? Instead of sprintf, I use string.format. Right? And whatever format you want, here's the format, there are the arguments, and it returns a new string. I don't need to malloc because I don't have memory management in Java. I don't need to free it up later, and I don't need to copy it because setting a string equal to another string is a simple enough matter. System.out.print, and I'll just print ln, and I'll just print my full name. There we go. Got to spell system correct though. And I get the same exact results. Right? So it's way easier because you don't have buffers, you don't have the low-level memory management that you have to have in C, and strings are almost first-class citizens in Java. Just like integers are first-class citizens, doubles are first-class citizens. They're not full first-class citizens because they still have to. They're still a class, but they're built into the standard Java library. Okay, Java language library. The second thing that we looked at was string tokenization. Right? So what does it look like in Java to do something like we did before? In fact, here I'm going to go ahead and cut and paste all this stuff. Same thing as before. There is my data, but of course I don't have char data array. It's just string data. Right? There we go. And I don't have to go through this process at all. I don't have to call string tokenization. If you want to split a string up into different tokens, there's a split function to do this. Now this is a regular expression. Don't worry about what that means for now. If you just want to split it on commas, then you say whatever delimiter it is. Right? And it returns an array of tokens. Right? Now what if you want to process those tokens? Well, you can go ahead and go into a for loop for int I equals 0, I is less than tokens, dot length I plus plus, because it's a regular old array, but oh man, arrays really suck. Right? System.out.println tokens sub I. Right? What's a better way of, and then you can see that here's the tokens. Right? What's a better way of doing this? Slightly better way of doing this would be for each string token in the collection tokens. And now you don't have to have an iterator variable. And you get the same results. If you're just printing them out because you want to look at them and you want to look and see that they're nice and pretty, then system.out.println arrays.toString tokens. There we go. And that's two deep string, but toString. There we go. And it'll print them out, not one to a line, but it'll print them out in this format right here. Yeah?
So in Java, it's possible to not only have an array of characters, but also an array of strings.
Oh yeah, yeah. Well, you don't generally want an array of characters. An array of characters in C is, of course, a string. If you want an array of characters, that sounds like a string to me. So in Java, just use a string. If you did want to split it up into an array of characters, let me go ahead and cut and paste this into the notes so that you have it before I go mucking with it. There we go. If you did want to split it, I want every single character because I want to process it character by character. I think you can do this. In fact, let's go ahead and get rid of this. Yep. You can. How did I do that? There's no delimiter at all, right? You can change this so that it's another delimiter, like O instead, right? And then BOU, both of the foos there is an empty token between them, and then it's not Omaha, but you can have this, or you can do it with. You're going to put me on the spot if you want to see this. I think it's O, lowercase o or capital O. Yes, I get it. Yes. Right. Now it splits on Omaha as well. Right. This is an OR symbol. Right. O or O. If you want to split on any A through Z, lowercase only, you can do that as well. Right. Now it gets really weird. Or if you want to go any A through Z, or 0 through 9, or capital A through Z, now I'm going to basically be getting a whole bunch of empty tokens now because I've basically taken out everything. Right? Yeah, just an individual character is like this. Right? Now if it's a special character like, I don't know, tab, I think that'll work, but I don't have any tabs in there, so tab, tab, there we go. And you see that it is split there, right? Right? Yep. It's retaining all the commas here. If you want other special characters, B plus, space space, tab, tab, space space, end line character. Or sorry, I should be doing tabs like this, not tabs like physical tabs. Tabs and end line character. I think this is how you do all white space characters. Yep, I think so. Otherwise, it might be W. I forget what's the difference. But there's one or more white space characters, and then this is escaping it out. Don't quote me because I don't remember. Right? Let's get rid of all that formatting. Let's go back to square one here. But you can do very powerful stuff. These are called regular expressions. Regular expressions are really powerful because you can do things like I want to extract anything that looks like a phone number, right? So 0 through 9. A phone number begins with 1, 2, 3, right? Followed by an actual comma or hyphen, right? Followed by 1, 2, 3, 4 numbers, followed by maybe a space and a space. So any white space character around it, one or more white space characters around it, one or more white space characters around it, and of course you have to escape these. And there. So that'll match a 7-digit phone number, and then you can go through an entire file and pull all these things out, right? Regular expressions are extremely powerful. We don't get into it in too much depth here, but if you want to keep it simple, you can just use a comma. But regular expressions are a tool that I would definitely encourage you to pick up. Okay? That's a tokenization. Tokenization, there we go. And the last thing that we looked at, of course, was string comparison. So for that, let me go ahead and grab my code over here. And how might we do that in Java instead? String A is equal to this. String B is equal to this. Right? And I don't have strncmp anymore. If I want to compare A to B, I can use, well, there is a string.compare. Compare. No, there's not. Okay, there is a A.compare to, right? B. Now, that's the ordering that you want. If you want to compare B to A, then of course everything will be switched around. But just like over here in the C version, if I'd called str comparison, oops, I thought I had it. Oh well. Oh, okay, I don't have it. I will make sure that it's in your notes, sorry. I did not copy that over. Don't worry, it's not lost. There we go. Here's what we had before, right? We did A and B, but if we did, of course, B and A, then we'd be comparing them in reverse. So here I'm comparing A to B, right? And I'm getting a result back here. And we can print out that one comes before the other, or that they're equal. And let's find out. What was the answer for apple and apples? Which one comes first? Apples. Careful. In this case, it's capital A, apple, comes before lowercase a, apple. Banana and apple, right? Remember that banana will come first because of the capital B. If you want to ignore case, compare, what is it? Dot compare to ignore case. And you compare it to B. And now apple and apple are going to be the same thing. They're equal. Okay? So all you need is dot compare to, or compare to and ignore case. You could do a byte limited version if you want to, but that just involves taking a substring. We have plenty of time if you want to look at an example. So byte limited versions. All you need to do, here's a case insensitive version. You do a.compare to ignore case B, right? And then byte limited version, you'd have to create a substring. Right? And what I mean by that is, let's go ahead and go with Apple Festival, right? And Big Apple, Apple City, I don't know, whatever, all right? And I want to compare, this part to this part. Well, I could take a substring, so string a sub a, right, is equal to a dot substring, a beginning index at 0, and then how big of a string do you want? 5, I think, right? And then sub b. Yeah, go ahead.
Is it not the ending index? It's how big we want it to be?
It's the ending index, yes. But in this case, I'm starting at 0, so how big do I want it? I want the up to end index minus 1, so it'll go up to index 4, but that means I'll go from 0, 1, 2, 3, 4, giving me apple, right?
Okay, I thought you went from 0 to 5.
Nope, in this case, 0, 1, 2, or in the second one, it's 0, 1, 2, 3, 4. I'll begin at 4. Oops, sorry, 4. And then I will go up to 4 plus 5 plus 1 to account for that ending early. So 4 plus 5 plus 1, so 10. Right? I think that's right. And then I will compare sub A to sub B. Right? And print those out. Apple Festival comes before Big Apple Festival. Of course, I'm printing A and B down here. That's not what I wanted, right? I wanted them to be equal because I'm pulling out this apple.
Could it be that you're also comparing space?
No, I don't think so. Well, let's find out. A is equal to sub A. We'll just go ahead and exchange them. B is equal to sub B. See what these are actually, the contents of these. I think I'm off by my math right here. Apple comes before apple, and there is so 9. There, finally. So 4, 5, 6, 7, 8, 9. Back one, it should have been 9. Right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 is where I want so that it goes back to 1, or not like that, but goes back to apple, right? So I'm comparing this substring to this substring, and I'm getting that they're equal. Right? You can do tricks like this. Right? Yeah, indexing, or you can write your, if you really want, well, I want a substring function that begins at an index and a length, right? Go ahead and write one, right? You can do that very, very easily, right? What if your length is 5, int length is 5, then all you have to do is I, and then I plus length plus 1, right? And int I will start that at 4, right? This is as general as it gets right here. And my length is 5. This will end up being the same thing. Sorry, plus 1, minus 1. There we go. Right. So you could like cut up a string. And I don't remember what the assignment 5 is this year, what I did for that, but typically what I'll do is I'll combine file IO and string processing and have you do something with DNA, right? Splicing DNA so that you have to take this DNA string and then translate it to a protein or something like that. That's what the hack in the main section is this week. Protein, you need 3 amino acids to generate a protein. So here's an entire sequence of DNA. Process it 3, 3, 3, 3. And it becomes really, really easy if you've got this kind of functionality right here. Right? All right. Any questions online? Doesn't look like it. So, any questions in here? No? Then what we'll do on Tuesday is we'll start on file IO. File IO is actually really, really easy because you already have all the tools at your disposal to do file IO. Because the standard input, mashing the keyboard, the standard output, printing to the terminal. Guess what the standard input is? Guess what the standard output is? They're files, right? When you write to when you print something to the standard output, you are printing to a file. So instead of printf in C, we'll use fprintf to print to a physical, like an actual file, right? In Java, what we'll do is we'll create a print writer, and then we can use printf. Or instead of system.out, we'll create a print writer and then call it whatever we want. My file dot println dot print format print for f. All right, whatever you want to do. Everything that you've already learned about standard output can be applied to file output. File input is a little bit more complicated, but it's just as easy. Where if you want to, we'll look at 2 ways of doing it in both languages: of processing a file character by character by character, or processing it much better line by line by line. And all you need to do with that is a scanner. You're already familiar with scanners in Java. In C, I will show you two functions. fgetS for getting an entire string from a file, or fgetC, get a character from a file. Right? Pretty straightforward. We'll probably be able to get it done in one day too. All right. Have a good weekend.